Welcome to the meetup. We're going to make a start now. So I'd like to welcome Lukas Lange, who's a research engineer at the Bosch Center for Artificial Intelligence, who will be talking to us about his new paper on SwitchPrompt. So slightly shorter meetup today. We're going to have a half-an-hour talk from Lukas, and then QA section will be moderated by Rajdeep Sarkar, who's joining us from the University of Galway. You should know the format by now. If you use the QA function to add your questions, so not the chat, but the QA function to add your questions, then when it comes to the QA section, Rajdeep will ask your question for you, or you can ask it yourself if you raise your hand. So raise your hand if you want to ask it yourself, and then we'll unmute you and you can ask your own question, which is always better. And you're much more likely to have your question asked if you do raise your hand. Otherwise, we'll ask your question on your behalf. So yeah, add your questions during the talk, and I'm going to hand over to Lukas now. Thanks, Lukas.
Yes, thanks for the introduction. I will share my screen. Let me know once you can see it. I don't know why is the share button disabled. I know it should be working. Just give me a short notice if you see it.
Not yet. Almost there, I think.
Almost. Okay, but I can already start talking. So thanks a lot for the nice introduction. I'm Lukas. I'm already here for presenting it today, but the most of the work was carried out by Gustava, who did an internship at the Bosch Center for Artificial Intelligence with us. He did most of the work, and most contributions are by him. But this is also joint work with Heike from our side and from June Araki, who is from Bosch Research North America. The paper is titled SwitchPrompt, Learning Domain-Specific Gated Soft Prompts. The actual title of the EASL paper is a bit longer, but this will do it for today. And this will be, yeah?
Sorry, still not seeing your slides. It says,
can't see it.
Oh, now yes, yeah.
Is it? I clicked the stop button. Is it now working or not?
Yeah, try again.
Let me try it again.
Yeah, that's good.
Okay, great. Yeah, I don't know what I changed. But yeah, this is SwitchPrompt. You can also visit this at EACL if you're on site. I guess there's also some online thing, but you will now get the full director's cut instead of the short version. And so I will tell you mainly 4 things today. Of course, I will give you an introduction. I will talk about the current pre-training, specialization, and fine-tuning paradigm of language models to solve your tasks. I will talk about prompting in general. And I will talk about SwitchPrompt, our method, of course, in more detail. And I will show you some experimental results. But let's start in the beginning. And I have to click with my mouse. So as always, everything starts with BERT. We have this as our foundation model. We can also use a different model as BERT. But it's important that we have one of these pre-trained language models. And most of you should be familiar with them. But the whole essence of these models is that you have a huge pre-training corpus, like BERT was trained on a collection of books and the whole Wikipedia, at least in English. And then you provide some self-supervised learning objectives like masked language modeling or also autoregressive language modeling. And you train a general representation of the knowledge that is in the books. And you can skip this step, but it helps a lot as you apply transfer learning. You transfer the knowledge that you gather during the pre-training, and you can make use of this in your fine-tuning task. The point is that you don't want a pre-trained language model out of the box, but most often you want to solve a specific task. This could be classification or information extraction or so many different things. So. And you don't take the plain BERT model, but you often apply some further training. So you gather the annotated training data and apply the task-specific training. And this works much better than fine-tuning without pre-training because of this transfer of knowledge. The major bottleneck that we still have here is that we usually have a lack of annotations. In practice, people tend to not annotate thousands of instances for each class or so, but they would rather like to keep it short and annotate only a few examples. And when you apply it to real projects, the lack of annotation is often a problem, in particular when you want to go to non-standard domains. And this is also the second problem, the domain gap between BERT and your task. Because language models like BERT might have seen a huge training corpus, but often this corpus is quite limited in their domains. We see a shift lately to just train on all what you get, but BERT, for example, was trained on Wikipedia and the books corpus, but your target application is quite often not Wikipedia. So you might want to process some newspaper articles or academic publications. So you have this domain gap between your pre-training and the fine-tuning phase. And in practice, you have to overcome this somehow. And one famous paradigm for this is the specialization of language models. There are like two famous approaches. You take a domain-specific pre-training step, so you gather a huge corpus of domain, so documents from your target domain, and then just apply the pre-training of BERT from scratch, or you take an existing model like BERT and continue the pre-training on your smaller domain-specific corpus. People like to do it actually because it works quite well. Examples that are quite famous are SciBERT, that was trained on scientific articles. We have BioBERT, trained on biomedical articles, and also ThoughtBERT, trained on task-oriented dialogue. And over the time, there is quite a large collection of domain-specific BERT models. And they overall follow all the same setup. You either specialize via pre-training, or if you have enough money, you can also do the domain-specific pre-training from scratch. And this way, you just incorporate the domain knowledge via unsupervised pre-training on domain-specific corpora. And why people do it and why are there so many BERT models is very simple, because it works very well. So you often get a huge performance boost when you do this domain adaptation via pre-training. But the downside, of course, is that you have to pre-train one model for each task. So it's one of the biggest challenges so far, that you have to adapt the model before fine-tuning. And when you go to a new domain, when you go to a new task, you would have to do the pre-training again. And you always need large collections of unlabeled data. I mean, you don't need a human in the loop in this process, just collect the data and do the fine-tuning. But it's expensive, and you also need massive compute power to do this. So it's clearly not optimal, even though it's working. So the question we ask then ourselves is if we can make more effective use of these general domain models like BERT, trained on wider corpora of general knowledge, if we want to apply them in special domains where we actually want to perform our target task. And this boils down to the question if we can just skip the second pre-training stage, the specialization, and just use the pre-trained out-of-the-box BERT model on our domain-specific task. And of course, there's also the second question that we always want to clarify is if we can achieve good performance with a small-scale data set. And in our setting, we ask ourselves if we can do few-shot training. This training setup where you have only a few examples per label and not a big corpus of 1,000 or 10,000 of annotated examples. And with the SwitchPrompt paper, we aim to answer both of these questions. So the most important method that we rely on to solve these questions is prompting, because prompting has shown great performance in few-shot training. And I assume everyone is more or less familiar with prompting, even though you might not know directly the term prompting itself. I mean, lately there has been this chatbot hype, and all of you, of course, have played with ChatGPT or whatever model. And prompting, as you can do in ChatGPT, works also for other models like BERT that are way smaller. But the answers, of course, are not that chatty. And the standard prompting example like here is you give a movie review that you gather from somewhere, maybe from some sentiment corpus, and then you ask the model to rate it. So you don't have like a classification head, but you just ask the model to give the answer with a token from its vocabulary. And this whole process is then called prompting. And it's like an emerging ability that we see in pre-trained language models, as this kind of using the language model is very similar to its pre-training. So we can utilize even more knowledge that the model gathered during pre-training for our task-specific training in comparison to fine-tuning. And this example from the previous slide is called discrete prompting. Here you formulate the prompt in a natural language phrase like it was, and then the answer that you get is also natural language. And the thing here is that a human has to design the prompt. You have to play around with the model, you have to change the prompt and experiment until you get like a desired output. This prompt is very small. This also depends on the model capabilities, if you can use like long and extensive prompting methods. But if you take a closer look at what's happening is that you have this prompt in textual form, and then the tokenizer converts the text into token IDs, and the token IDs in the first layer of the transformer get converted to vectors, so the embedding representation. So in the end, you just input embedding vectors into the transformer model. And what we have observed in the past, I mean, we do machine learning, so we can train vectors based on labeled data. So we don't have to manually design it, but we can just ask an optimizer based on labeled training data to train vector representations. And this is then the so-called soft prompting. For this, you don't input like text anymore, but you have a vector sequence, which is often randomly initialized, and then we train it with standard training on our task-specific data. So we can utilize still training data, we can utilize human annotations, and we don't have to design a prompt manually, but just let the model train a prompt. So we are also not limited to the prompts that are in the vocabulary of the model, and just let the model do the job. And one famous example of this soft prompting, which is also often called prompt tuning, is from Lester and colleagues. It's like the very basic thing what I've told you before. So the soft prompts are the orange, yellow vectors, the H vectors. I have shown you 4 of them in the last slide. It's an hyperparameter in the end that you can control. So you can have an arbitrary number of prompts. It might also be depending on your problem. If you require more complex prompts, or if the problem is simple and you can go with 1 or 2. And then you input the prompt at the embedding layer level and also in the first layer of the transformer. The rest of the model is not trained, so you only train the prompt representation. And so you also see the transformer has so many parameters, but 99% of them are fixed. So you can train the model with a way smaller set of training examples because you don't have these large amount of parameters and can just focus on the prompts. So therefore, it's obviously suited for few-shot training, where you only have a couple of examples. Okay, this is the standard prompt tuning. I think almost simultaneously, a different research group in this project from Leo et al. Came up with a slightly more complex prompt model. Here, the prompts are based on a prompt encoder network. So it's not single vectors, but like they have a huge LSTM network in the back. And they also train the language model. So they train just everything they have. And they observe greater performance gains when you have large training data sets. Obviously, more data, you can train better models, and you can also train more parameters. But the idea behind this is quite simple and very similar to the prompt tuning on the last slide. But they also noticed in few-shot settings, training the whole model is not good. So they came up with the so-called p-tuning version 2. This is the most important prompting method for today. So they reverted some of their changes. They removed the prompt encoder network We have a simple vectors again that are more easy to train. We keep all the language model layers frozen. But instead of injecting the prompt into the first layer of the transformer, we now inject the prompt into each layer. So we don't have access to the layer, to the prompting information in the first layer only, but during the whole march through the transformer, we had all the information that is relevant to solve this task. And what's also important is they don't have this language modeling head as the output anymore. They replaced it with a label with a head for the class label. So it's more or less a standard classification model now. And we can fix the input and train it like we want with the training data. And this prompting method works quite well in practice. So we used it also in our SwitchPrompt. And we made a small analysis for you to convince you that prompting is actually good. And we did a 4-shot experiment on clinical question classification. 4-shot means that you have 4 examples per label. This data set, I think, has 6 labels, so we have 24 instances. And that's the whole training data. We train a model on 24 sentences. And you see that the BERT model, I mean, it's able to solve this task better than random, regardless of the method, because we have this transfer learning from the pre-training. But you also notice that the fine-tuning is much worse than the prompt tuning version. And this is because you don't have to train the whole model with the prompt tuning, but only adjust the prompts according to the small training set. This was the general domain BERT model, but this is the clinical question classification data set. So we also tested the clinical BERT model. The fine-tuning now works a lot better because the model is already adapted to the domain and you have to tune the parameters less. The prompt tuning also benefits from the domain specialization. So I guess we can conclude that domain specialization is important. It's super important for fine-tuning, but it's also important for the prompt tuning. But we want to avoid this specialization step. So the question we tackle with SwitchPrompt in the end is, can we basically specialize the language model without the LM pre-training step? And the answer is that we specialize the prompt instead of the model. So we provide a domain-specific prompt to a general domain model and want to achieve the same performance with compared to a domain-specific model. And that's the whole essence of SwitchPrompt. And the general SwitchPrompt architecture is here on the right, but I will show you this in more detail now. And we are considering mainly 2 points when thinking about how can we specialize a prompt to the domain and not the model. So we still need to give some information on the domain that we want to target in our task to the model. We put this information into the prompt and then the model can decide what to do with it. And it's actually important that we, on the one hand, input this information, but we also give the model the option to decide if it wants to use the domain-specific information or not. And the domain information that we gather here is based on domain-specific keywords. So for our target domain, we have some documents, might be from the training data or some unlabeled data. Doesn't matter if there are labels or not, because we can then extract keywords that are representative for this domain or also for this task. And we can do this unsupervised. And then we just take the keywords that we extracted and extend the soft prompts that we have anyway with these keywords. So what we had before is this soft prompt vector, the v1 up to vn, and we add our keywords. We add the keywords either as a suffix or as a prefix. And I mean, both has some advantages and not, but again, we let the model decide what it wants to use and when it wants to use it. The keywords itself, I mean, we automatically extract them. We don't do it manually. We are machine learning people. So we use maybe an old school method, but it works quite well. So we use the TF-IDF score. For each term in the target domain documents, we compute the term frequency and the inverse document frequency. and then we assign a score for each term, like the domain relevancy. The method is old, but it's proven to be quite robust. The good thing is we don't have to train any machine learning model, but we can just use our data. We can apply this method to any domain. And we started out with TF-IDF, but the results were actually good enough that we can use it in practice, so we stayed with it. So here are the example keywords that we extracted for the clinical domain. We get like verbs like diagnose or prognosis. All of them are medical terms, so you see they are actually relevant in the medical domain and representative for this. We also did it for the material science domain. I mean, at Bosch, we are working a lot with solid oxide fuel cells. So we have this data set on material science publications. And you see that the keywords that are like most highly ranked are fuel and oxide. So very, very specific for these documents and also very representative. Many technical terms are extracted here, like ion conductor or electrocatalytic. So the keyword extraction works just fine. So we stick with TF-IDF and use this to extract our keywords. And based on these keywords, we can create the domain-specific prompts that we can then use in the prompting model. Okay, so part one is the creation of the domain-specific prompts. You've seen how we extract the keywords and add them to the prompt. Now we still want to let the model decide if it wants to use this prompt with the domain-specific information, or if it wants to use the general domain model on prompt. The thing is that some instances in the training or in the test data set might be easier to solve and don't require any domain knowledge. And some very specific questions might be very complex and require this domain knowledge. So in that case, the model should use the domain-specific prompt instead. We introduced some gates for this. These are trainable layers in the model. We train it together with the prompt vectors. And with these gates, which are basically network layers, the model can control the influence. Specifically, the standard p-tuning version 2 looks like this. We have the general domain prompt, which are just the v vectors without any keywords, without anything that goes into the model. We add the domain-specific versions. In particular, we add two ones. We add the domain-specific suffix prompt, and we add the prefix prompt. And then we introduce a gate. And with this gate, here G2, the model can decide if it wants to use the domain suffix or the domain prefix prompt. So it can control the influence of the prefix suffix style prompts. And we introduce a second gate that lets the model decide if we want to use the general domain prompt or we want to use the keyword. So we give the model the freedom to control how many keywords should be in the prompt or if it should stick with the general domain prompt. And this is all based on the training data. So the prompts and the gates are randomly initialized and then learned during the future training. Overall, you see we give the model much freedom. We help it by inputting helpful information, but we don't force it to use this information. And you also notice SwitchPrompt is more or less independent of the particular prompting method. We have a method that can prepare a domain-specific prompt, and it can be used in also other prompting methods. We use it in this p-tuning version 2, but we could also use it in the version 1 or whatever other soft prompting technique comes up. And that's the essence of SwitchPrompt. Now that you have seen the SwitchPrompt method, let me show you some of our results here. And I talked already about the clinical question classification. We first started with a standard question classification dataset. This is from the general domain. It's the TWAC dataset. I mean, this was originally created for question answering, but they also assigned a category to each question. So the task is to assign each sentence or each question to one of these 6 categories, like when did Hawaii become a state? The answer is obviously related to a year, so it's a numeric number. And The overall task is quite simple, but it's interesting because we have an equivalent in the clinical domain. So there we have the GARD data set. It's also question classification. The input format is the same. So we have a question and a label. Again, we have 6 labels, but the questions itself are very domain specific. Like you have all these technical terms in there. So it's much more complex, and you see that a model that should solve this can really benefit from having this clinical domain knowledge. And it's a cool way to study the influence of domain-specific information or not when you have these paired data sets. And then we also used the SOFC experiment data set. This is the material science data set. It was built on publications from the material science journals. And each sentence is annotated with several things, but we focus on experiment settings. So it's a binary sentence classification task, whether a sentence contains an experiment or not. So all of these are sentence level classification tasks. The question classification data sets have 6 labels, and the right one with the SOFCs has 2. It's a binary task. And here are the results. At least for the domain-specific ones. Here are the clinical question classification and the material science sentence classification. For each model, for each setting, we use the general domain BERT model and test the different methods, like we have the fine-tuning, we have the p-tuning version 2, and our extended version, the SwitchPrompt, that introduces the keywords for each prompt. There are several observations we can make. First, the SwitchPrompt is consistently better than the p-tuning version 2. So regardless of the number of shots, if we use 2 examples per class, 4, there are also some more numbers in the paper. We have also tested, I think, 16 and 64 shots, and it was consistently better than the standard p-tuning. So we don't lose anything from including the keywords with SwitchPrompt, but we can only gain something. And in every setting, we also see that the prompting-based methods clearly outperform the fine-tuning. So we can show that prompting for future setting is a lot better than the fine-tuning. This was the general domain BERT model, but let me compare to the domain-specific model. So it's the clinical BERT for the GARD dataset. It's the SciBERT for the SOFC dataset. Because we wanted to clarify whether we need the specialization step of the language model, or if we can just skip it and use the SwitchPrompt for the specialization. The picture is a bit mixed here because you see red colors and green colors. So sometimes the domain-specific model is better. Like if you go to the SOFC experiment, then for 2-shot and 4-shot, it's better to use the SciBERT instead of the general domain BERT. But you can also notice that the gap between SwitchPrompt and the domain-specific p-tuning is quite small. So it's an effective way to reduce the need for domain specialization of the model. We can easily just specialize the prompt with SwitchPrompt and get a comparable results. And this is good because now we don't need to train a new language model for each and every domain that we encounter, but can just train a general domain model. We might also want to focus more on this general domain model because we can easily adapt it now. A last experiment we also did was a SwitchPrompt with the specialized model. This time we have the specialized language model plus the specialized domain. It's the best model in all of our experiments. So specialization helps a lot. More specialization helps even more. But that's not what we want to have in the end. So the main takeaway from here is, I guess, that you can use SwitchPrompt with a general domain model and can apply it to domain-specific tasks. But you can also improve domain-specialized models. And we assume it might be that the keywords are not only representative for the domain. We took the keywords from the labeled datasets. So the keywords might be also representative for the specific tasks. So we did an experiment with our SwitchPrompt on the general domain question classification dataset, where we would assume that the influence of keywords is rather small, because you don't need any domain knowledge to answer these questions, or you don't even have to answer them to categorize them. But the difference between the switch prompt and the p-tuning here is even larger than in the domain-specific settings. So we assume that the keywords also carry information on the task. And again, it helps to introduce additional information into the model. And in the end, it might not even matter if it's domain information, if it's task information. We just introduce information that is relevant for the task to solve, and the model benefits obviously from it. So keywords are a good thing to have in the model. And lastly, we also did an ablation study. This is just a short snippet. The full ablation study is in the paper. Also, the other more detailed results are in our paper. You can find it online. This ablation study was conducted on the clinical question classification dataset. We have the full training data, so it's not a few shot, it's a very high shot data. And we found that if we remove these keywords from SwitchPrompt, so just use the p-tuning version 2, we have a performance loss of 1.6%. So including the keywords is really nice. We get a performance boost from it. But this is also very interesting if we change the way how we include the keywords. So if we don't concatenate the keywords and the prompt vectors in our prefix and suffix method, but simply include both independently, we lose a 3.3% performance gain. So in this setting, having the keywords is worse than having no keywords. So it's obviously very important to have a method, to have a good method to include keywords and not to just throw them into the model somewhere. We observe the same, even more extreme, if we remove the second gate. This one controls if we want to use the prefix or the suffix domain-specific prompts. Here we lose 4.7% performance. So I think the main thing we can take away from this ablation study is it's super helpful if we have the keywords correctly included, but a simple inclusion might not help you in this setting. And taking away this freedom from the model with the gates and the concatenation is not a good idea. And lastly, we also did an ablation study where we just included the keywords and removed all of the soft prompts. So the model totally fails to perform good. So we have minus 35% decrease. This is obviously not something you should do. So if you do soft prompting, you also should include soft prompts and should not only rely on keywords. But yeah, that was quite obvious. Okay, that's already it from my side, I would say. Then let me give you a small conclusion. I hope I was able to convince you that with SwitchPrompt and also with other methods, that we can efficiently adapt generic language models like BERT that are trained on standard domains for applications in these special domains like clinical documents or also solid oxide fuel cell documents. So something that is very far away from the pre-training without continuing the expensive pre-training. But this is a very important point because we can do quick experiments in new domains and don't have to train a language model first. These models, in particular the prompting models, are very good for few-shot settings because this is one of the cool properties of prompting. And now we can also combine prompting with domain specialization, but it also works in the full training data. But the difference is smaller compared to fine-tuning. And overall, what you have seen today is the SwitchPrompt method. You've seen the way how we integrate domain-specific information with keywords into this. We let the model decide which information to include over the gates. And today you have only seen experiments where we included in the p-tuning version 2. I mean, it's totally independent of the soft prompting method. So we might also apply it to a p-tuning version 3 or whatever comes up next. So I think that is a very important point that speaks for our SwitchPrompt. And lastly, this will be presented at EACL next week. So if you're on site, feel free to join our poster session. I think Gustava, the main author of this paper, will be presenting it. I will also join, and then we can also have a discussion there.
Thanks
Okay,
so much.
then thanks for listening in.
Thank you, Lukas. It's good talk. I'm gonna invite Rajdeep now to conduct the QA.
Yep.
Rajdeep, over to you. And
thanks, Lukas. Yeah.
Sorry to interrupt, Rajdeep. Just going to say to the audience to keep adding your questions to the QA function.
Yeah, thanks, Lukas. This was a very nice work done at Boss Research. I thoroughly enjoyed it. This is a very interesting work, and myself working on domain adaptation of chatbots. I find this really interesting. One of the initial things I noticed was when people use prompting or soft prompting in language models is that they notice that the performance increases when the number of tunable parameters in the prompt tokens increases. So, do you think the number of keywords, which is M, or or the number of prompt tokens, which is N, if they are varied, will impact the performance of the model substantially?
Yeah, that's a good question. Both are hyperparameters and both affect the model performance. So we have one ablation study in our paper where we varied the number of keywords that we include, and it got better the more keywords we included, and then it stopped at 6 or 7, and then decreased the performance again. So there's always a sweet spot, and I think this is highly related to the amount of data. So when you have like lots of training data, you can have more keywords, you can have more prompt things. You could even train the language model itself and get a better performance. But when you have 2-shot or 4-shot settings, then you need fewer parameters to train because you don't have enough training signals.
Oh, okay. Yes, I think selecting these hyperparameters is extremely important because we want to definitely have a sweet spot and not include noisy tokens inside the prompt, which might dictate the performance. One another thought I had was, suppose we have access to quite a few domain-specific documents, for example, clinical PERT uh, or for example, material science, and we fine-tune the BERT model using masked language model. Do you think using that as a precursor to soft prompting would be helpful in there?
I mean, we have the numbers here where we show that it's actually helpful. So in the bottom part of this table, you have one of these specialized models. And you can compare the numbers also for the p-tuning version 2 or so. And you will find that this specialization definitely helps.
Okay.
So if you can afford it, it's also still a good idea to specialize the domain model.
Okay. This is interesting. Okay, and do you if I do not have any pre-trained, like if I want to pre-train a language model on domain-specific data, what amount of data would we want for proper domain adaptation in the fine-tuning phase, and also how many few short examples like you found that was good enough to have a very good performance if we do not have fine-tuning data present?
The first part, was it referring to the number of sentences for the pre-training or for the?
Yes.
I mean, in the pre-training, it depends if you pre-train a language model from scratch. So if you take an existing checkpoint like the standard BERT, then you obviously have all this basic language knowledge in there and just the domain adaptation. Then we had some experiments in different papers, and we think that if you have a couple of 100 megabytes of text, then it can also can already be enough. Having more is obviously better, but 200K sentences or so might also be sufficient.
Okay.
For the two-shot prompting, this is highly task specific. We have like quite a simple task like question classification, which is more suited for few-shot prompting. If you have like summarization or something like this, the more complex your task, the more training examples, as always. But in the end, it's very hard to make a general statement. So you see here, for example, that it's easier for the clinical one. We get 50% performance. It's better than nothing. It's far better than random. We have 6 classes, so we have actually a useful model already. So it depends on what you need in your application.
Okay.
If I can just ask a question on this slide, Lukas, have you done any comparisons with some of the really large language models like Llama or GPT 3.5 or whatever on these days?
We have internally, of course, some with them, but they are not part of the SwitchPrompt paper.
So can you shed any light on that? Broad terms.
In general, I think the larger language model, the better is also the zero-shot or also the few-shot generalization. It's remarkable that they can do zero-shot at all. So the less training data you have, the more important it's to have a better model.
If you had to make a direct comparison on using these data sets on let's say two-shot.
I'm sorry, I don't have any concrete number in my mind.
And do you have even a ballpark idea? Like, will it be better than the fine-tuned domain-specific with SwitchPrompt? Percentage points, 10 percentage points, or?
I really don't know. Sorry.
Because I guess that's what everyone cares about.
It's something you can quickly compute. Two-shot, it's what, 12 examples. You can compute the performance in 2 minutes. But I'm sorry, I don't have any concrete number in my head.
Okay, thank you.
Lukas, as you said that we might need a few more examples for tasks such as summarization. Was any such experiments carried on in the question answering or summarization task?
In our research group, we usually do information extraction. So the more complex tasks are then relation extraction or so. There we have a successful application of prompting, also based on the label description and the relation description and things like this. So I'm really no expert on summarization. It just came to my mind.
Okay.
And another question on the ablation study. You mentioned the results on one data set, but I think you said that you also did some ablations so you got some ablation results on different data sets as well. Well, did you get the same results across the data sets? So is this the pattern that you see across all of the data sets?
Yeah, it's more or less all in the same direction. The numbers are not one-to-one, but we see that without the keywords, we get a loss. But the loss is even worse if we have keywords, but a bad way to include them. And this was consistent over all the data sets.
Thank you.
That's also a point why so Gustava was working on this during his internship, and it took quite some time to find a robust method to actually include the keywords, because it's not that easy to actually have them in the prompt.
Mm-hmm. Rajdeep, did you have any more questions?
Yeah, I have a follow-up question on that. Do you think methodologies such as topic modeling might help to select better keywords as opposed to TF-IDF scoring in this case?
Yes, I would assume so. Also some generative method to get keywords. These are really like extracted words from the text. but you can make better keyword extractions that generate real text or whatever. So yeah, it's obviously some future work to explore the keyword generation or extraction.
Okay, sounds quite exciting. Line of research.
Could be your next paper.
Yeah.
Rajni, do you have any more questions?
Yeah, I am. There is one question. I think Mayank is asking if keywords are special tokens or just normal tokens from the documents. Are they specifically terms or just words with some higher weights in the TF-IDF scoring mechanism?
About the keyword that's actually extracted. I mean, these are all words that are found in the documents and that have quite some high term frequency, so that appear quite often in the clinical documents and not that often in the general domain documents. So these are all real tokens from a text.
Okay. I just wanted to like we can use, for example, adapters to adapt a language model to a specific domain. Do you think SwitchPrompt in conjunction with adapters would be beneficial?
Yeah, I would actually say these two would combine quite well. So we have seen with SwitchPrompt that it still benefits from an adapted language model, and that an adapted language model still benefits from SwitchPrompt. And as adapters are also like some clever way to adapt the whole language model, I think it's a good thing to combine them as well. Yeah.
Yes, that sounds interesting. And did you find any special cases where this methodology failed, like it was not able to identify special cases of sentences or categorize special cases of sentences there?
No, I mean, we have an error analysis in the paper. I don't have it on my slides, but you could check it out. There are some categories where it was worse, but some systematic things, I guess, in the paper.
Okay, I'll definitely give it a look.
I saw that there was a follow-up question from Mayank. Mayank, would you rather just ask a question yourself? If you put your hand up, I can unmute you, and then you can clarify your question. Great, thank you.
Hey, can you hear me?
Yep.
Yes.
Cool. So yeah, my question was like, because like we are talking about domain adaptation specifically, and when we get like a very frequent keyword that is used in some different domain, if like because we are adding this as a prefix or suffix, and this new token might split a lot if it's from a different domain, right? If the original bird has not seen it in the category, this token might split a lot. So that's why my question was like, do you add this new like tokens as a different vocabulary tokens? Because like I think we can add those special tokens, right, during fine tuning sometimes, or is it just a normal token so that it splits or it doesn't split, and would it make a difference?
That's a great point. We didn't do it in this paper, so we take the splits as they are. We have some follow-up version with domain adaptation where we considered the tokenization problem, and it's actually possible to easily get a new token and get a good representation for that token. And it's I think we didn't think about it for SwitchPrompt, but it's certainly something we could do here as well.
Cool. Yeah, thanks.
Hey, Rajdeep, should we finish up?
Yeah. I think this is a very interesting work. I will definitely talk to Kostav more about this, and I'll also read the paper and go through the analysis and see try to think how to make things work in cases where it's failing, and how to combine SwitchPrompt with adaptive language models. I think that's a very interesting line of research I would ideally want to explore as well.
Yeah, I think the combination with different methods, also with the tokens, I mean, they go really good jointly, so it's a good direction, yeah.
Fantastic. Well, thanks so much, Lukas. Really, really interesting talk. And lots of thanks to Rajdeep as well for conducting the QA session. That's really a really interesting session. And thanks to the audience for coming. And I'll see you on the next one. Thanks a lot. See you soon. Bye-bye.
Bye.